In this video, I wanted to work an example unit conversion problem where you have to use some governing equation and you're given some parameters and you are asked a question, to answer. All right. So here's the question. This is, typical of what might show up on an exam. All right. So the question is, what is the electrical resistance for copper and for aluminum for a 1,000 foot run of AWG 8 wire? Okay, I should tell you that's wire. AWG stands for, I think, American Wire Gauge. And there's different numbers that you use, and you can look up essentially the radius of the wire or the diameter of the wire. And from that, you'll be able to calculate the resistance based on the physical properties of the metal that you're using. Okay, so how would you get started? This is essentially the given information. Okay, let me go through that. We know we have AWG8, and the diameter of AWG8, you look that up on Google, and it turns out to be 0.1285 inches. Okay, pretty thick wire. All right, then on an exam, of course, I would give you the governing equation. Resistance turns out to be in ohms. That's a unit you're not used to working with, but that's okay. This is about units. It's not about any particular type of problem. All right. Then I looked up what's called the resistivity constant for copper and for aluminum. And, it was a strange kind of thing that I stumbled upon first. And I thought, well, this is a happy accident because this is the kind of thing you find in engineering. They gave the resistivity of copper to be 0.0171 ohms per millimeter squared divided by meter. Okay, so if we think about that in terms of base dimensions, what we have is an L squared on the top from millimeters, and it's a different L, but it's still L nonetheless. It's L on the bottom. And so you would expect resistivity to be ohms times length, or ohms times meter. All right, and it usually is, but there's some reasons it would be specified in millimeters squared per meter, because sometimes you can look up a table and it's got the cross-sectional area of the wire. It's already in millimeters squared. And so that would make an easy, you just multiply these two numbers together and you can find the resistivity. Okay, so that's neither here nor there. You can still work the problem even if you're given something that's non-standard units, because we know how to convert units. All right. So at this point, what I would like you to do is pause the video and give it a shot. Try it on your own. See if you can calculate the resistance of a 1,000 foot length of wire that has a diameter of 0.1285, given that this is the equation. Okay, so pause your video and give that a try. Okay, so after you've tried it, maybe you got stuck, but maybe you didn't. Let's think about this. All right, so we're trying to get the governing equation, R. R is equal to rho times the length over the cross-sectional area. All right, and we see some units showing up. I see millimeters in the millimeter squared in the top, and I see meters in the bottom. All right, and so as I'm thinking about this, it looks like if I had length in meters, okay, meters here on the top divided by meters on the bottom would cancel. All right, so my goal here is, the way I'm thinking ahead on this is I'd like to get the length converted to meters, okay? And if you use the same argument for cross-sectional area, what would it be? What are you shooting for cross-sectional area? Well, for cross-sectional area, I have millimeters squared. If I did that, then the resistivity, which shows up here as millimeters squared over m, that would cancel. Okay, so I have a goal in mind at this point. I want to convert L into meters and cross-sectional area into millimeters. Okay, so let's go ahead and start that with length, and we'll come back to area. Okay, so my thinking then is I start with what I know, 1,000 feet, and I'm trying to drive that into meters. Okay, and typically I'll give you some conversion factors, and one of the conversion factors that I remember is that there, in 1 foot, there's 12 inches. Okay, you should probably memorize that one. I realize if you're an international student, English units are weird to you, but please just try to memorize some of these things I tell you, so that things will go smoother for you. Okay, so memorize 12 inches in 1 foot, and then I have in my memory bank that there's 2.54 centimeters in 1 inch. Why did I write centimeters on top? Because I wanted this to cancel. Why did I put 12 inches on top? Because I wanted the feet to cancel. All right, so I have these conversion factors that I remember, and I can write those as ratios and drive this to the direction that I want. Okay, so ultimately, I also know there's 100 centimeters, because I know prefixes, 100 centimeters in 1 meter. And so everything cancels, and I get this value of L converted. Okay, so I could plug that into a calculator and find out the answer. All right, I'm not going to do that. I'm just going to store all these results and plug it all in at the end. Okay, next, cross-sectional area, and I know it's a wire, and it doesn't take much of a thought experiment to envision cutting a wire in half, and what you get is a circle. All right, and you need the area of that circle. So that would be pi times the radius squared. Pi r squared is the area of a circle. But we're given diameter, and so we just take the diameter, divide it by 2 to get the radius, and we square it. Okay, and our goal here is to get this in millimeters squared, so that we can plug into this formula and the dimensions will work out. Okay, so if I have D in inches, what was that answer? 0.1285. That's in inches. I'm trying to drive this conversion into millimeters. Okay, and then when I plug that in, I'll get millimeters squared for the cross-sectional area. Okay, so what I know is that there's 2.54 inches in 1 centimeter. And then if I think about it for a while, there's 1,000 millimeters in a meter and 100 centimeters in a meter. Those are off by a factor of 10. So in 1 centimeter, I have 10 millimeters. Okay, so think through that. Does that make sense? Hopefully you'll get faster at this as you practice. Practice is important. Okay, so we see inches canceling, centimeters canceling, and I get an expression for the distance. Okay, I can plug that into this equation, and I would get the cross-sectional area. And finally, I can plug everything in. I know what rho is. I know rho for copper. Let's go copper first. Rho is 0.0171 ohms, millimeters squared over meters. I plug in for length. Okay, I get L, that's in meters, so I'll put that in parentheses so I can cancel the units. And I divide by A, which I know. A is in millimeters squared. And those units cancel, and I'm left with ohms, which is the units for resistance. Okay, so I've plugged all that into a calculator, and I get, let's see if I did it right, 1,000 feet, I get 0.62 3 ohms. Okay, so I carried this to 3 decimal places. You could do fewer, but there's the answer for copper. Okay, so if I wanted to change that for aluminum, then the only thing that changes is the resistivity. All the other dimensions don't change, and so and you get a value of Ra is 0.965 ohms for, you could write this as per 1,000 feet, because that's what we calculated it for. Okay, so hopefully this helps you. What I'm going to do next, I'm going to show you a way to check your answer in MATLAB, okay, using the symbolic capabilities for units in MATLAB. Okay, so at this point, I would like you to, hopefully you've downloaded MATLAB and you can run it, and then the first thing you do, let me just start over. Go to New, Live Script. I want it to be a live script. Okay, so it's going to show up as untitled, and you can save it as something. So, unit example 1. Okay, so save it somewhere, and this example shows you how to use part of the symbolic toolbox from MATLAB, and it has units embedded already in it. So I've already worked out this, but I wanted to show you how it works out. Okay, so the key here is to come up with the symbolic class, is what they would call it technically. You don't need to know that, but the variable you declare, u, matters, and we'll see why in a second. So you're going to start out this example with just pasting that in. Well, u is equal to sim unit. Okay, and that tells us in MATLAB that u is going to be designed to add units to different variables. Okay, so in our example, we were looking at d. We had d is equal to 0.1285 for the cross-sectional diameter of wire. And that would be multiplied, just like we did on the page. We multiplied by the units. Okay, so u is the variable, and then we put dot to tell us what units to use. So dot in gives me inches. Okay, and then if I run this, it will tell me 257 over 200 inches. Okay, so what's going on here is it's trying to represent this with as much precision as possible. That's part of the symbolic features of MATLAB. Okay, so it's converting this into a rational number, which is exactly equal to 0.1285. Okay, we'll talk more about that in a second, because that becomes a little bit irritating. Sometimes we'd rather just see the number instead of the rational representation of the number. Okay, but it gives me diameter. Okay, the other thing I could do is I could give it length, and I have 1,000, and then what would I put next? Well, I want to add a unit, so it's times u for the unit variable, right? And then I want to do feet. You notice it's got this completion part to it, so you choose feet. And we hit run. Okay, so next we have the density, the conductivity of copper that we can put in, and we know that number is 0.0171. And we multiply by the units, u dot, well, that's ohms, and then I did u dot millimeters, so you can use prefixes, all right? And then you can square that. So the shift 6 gives you the squaring operator in MATLAB. And you can divide by units of meters, okay? So when I hit run, that runs and it shows me the units showing up here to the right on the screen. It converted it to a rational representation, ohms times millimeters squared divided by meters, okay? So we put all the units in for everything that we're working on. All right, from there, I could calculate the resistance of copper because I know it's rho times the length divided by the area. Okay, and if I hit, well, I need to calculate what the area is first before I do that. Area is pi times r squared, okay, but r is d over 2. All right, so we enter the formula into MATLAB and hit return, and we get answers back, okay? Now, it's interesting because we look over here and we see these units, you know, they're specified, there's no simplifications that have taken place, all right? All the units just get plugged in and, you know, it's just a mishmash of units, okay? So what we know is that these things can be converted and represented into a certain unit system, okay? So what I'm going to do next is I'm going to say unit convert, okay? And what I'm expecting is my answer to be in ohms. So I can do u dot ohm. And if everything is working right, it should give me the answer in ohms. And in fact, it does, okay? So you see it's this crazy representation to try to keep as much precision as possible. It doesn't even unfold the pi, right? It's keeping pi as a symbol rather than a numerical value. Okay, so that's a little irritating. So one thing you can do at the very end is use this MATLAB function. You don't need to know how it works, but it tells you VPA, you put parentheses, and it stands for variable precision assignment or something, VPA. It's going to give you a numerical representation. So I can just do VPA of RC and hit run, and it gives me the answer that I had before. But look how many decimal places. It's trying to carry as much precision as possible. And we know that the, you know, way out in here is not, these aren't significant digits. And so we can control how many decimal places show up. Like if I only wanted 3 decimal places, I could put comma 3 and I'd get the answer that we talked about previously with the fully worked out problem, okay? So I'm a little hesitant to show you this because it seems so easy to make these unit conversions. You need to be able to do these things by hand, okay? So that you can think through this and practice and get good at it, all right? Because you won't develop any intuition about how things work unless you do these things yourself. But I did want to show you, I decided it's worth it to show you because you can check all your answers and you can invent as many practice problems as you want, okay? So if you're having trouble with unit conversions, just think of something and then you can try it and check your answer in MATLAB, okay? Obviously, it's, you know, easy to change things. So if I said, well, what if I had 1,000 meters? If I had 1,000 meters of wire, you know, that's longer than 1,000 feet. I rerun that and I get a larger value of resistance. Okay, so you can see the value of having this being handled programmatically. We can change units and everything just trickles through and gives you the answer at the end, okay? So take a look at that, type these along in and be able to check your work, and I think you'll find that really useful.